Okay, so today we are going to discuss about immobilized metal affinity chromatography. Okay, so from our purification chart, we can see this is a step in our capture stage of protein purification. Okay, so in our last class, we discussed about sample preparation, which was the first stage of protein purification. This is the next step where we try to capture protein of our interest. Okay, so how we are going to do that? So IMAC is called immobilized metal affinity chromatography, where a nickel ion is immobilized in a purification matrix. Okay, and protein, those which has a hexahistidine tag that has affinity for that particular nickel immobilized matrix, and that's why we can purify only histidine tag protein using a nickel IMAC chromatographic method. Okay, so as you can see here, this is a protein, and by using recombinant DNA technology, we can put a histidine tag either in N terminal or C terminal of that particular protein. Okay, so histidine tag, the most efficient histidine tag is 6, contains 6 histidine. That's why we sometimes call hexa histidine tag. Okay, but for some cases, people still use, like, 8, 9, uh, 10 histidine in histidine tag. Okay, but like in general, we normally use 6 consecutive histidine residue in hexahistidine, like histidine tag. Okay, and how we produce a histidine tag protein? So we have to do a recombinant DNA technology method to produce a hexahistidine tag. So we have different vectors that already contain his tag. So once we put our, like, gene of the protein of interest and then overexpress that particular uh, uh, construct inside bacterial cell, it will produce the protein with a covalently linked histidine tag in it. Okay, so now, as we discussed, like, using a IMAC, nickel IMAC, we can purify histidine tag protein. So what would be the matrix? So matrix is nickel NTA matrix, or nickel nitrilo triacetic acid matrix. Okay, this is the full form of NTA. So as you can see, the normally a nickel column looks like this. Okay, so you see the uh, pale blue color. This is because of nickel 2 plus ion. Okay, and this is the way how nickel matrix interact with his tag protein. So you can see this is the inert part of the matrix, and there is a spacer arm, and then the NTA ligand. Okay, nitrilo triacetate ligand. This part is the NTA ligand. Okay, and this is the hexastine tagged protein, and you see the nickel is coordinate covalently linked to the NTA ligand, whereas 2 histidine also making coordinate covalent bond with that particular nickel ion, and that's how protein binds nickel matrix. Okay, and this interaction is highly specific. So protein which don't have hexahistidine tag, they don't bind nickel matrix in such strength of interaction. Okay, so now we know which protein would bind IMAC and how the matrix looks like, and how the protein interact with the nickel matrix. So next is, what is the process of purification of his tag protein using a nickel NTA matrix. Okay, so you can see the first step, what we discussed, that the preparation of the sample and lysis of the cell, where the protein get extracted from inside the cell to the buffer. Okay. So if we are using a denaturing condition, so the protein will be denatured. If you are using a native condition, then protein will be in folded form. So then what we have to do, we have to uh, like pass that solution through a nickel matrix. Okay. So in that condition, the column would bind specifically the protein that has histidine tag, and in the flow through we'll get the protein which don't have hexahistidine tag. Okay. And then there would be some protein which don't have hexahistidine tag but still might interact or get entrapped inside the nickel column. So what we have to do then, we have to wash that column, okay, to remove all the unnecessary unwanted impurities. Okay. So after washing, you see, only his-tag proteins are bound to the column. Then at the final stage, what we have to do, we have to elute those bound protein, specifically bound protein or his-tag protein. So that step would be called uh, elution. And then you see, we have started at the beginning a mixture of protein, and then after elution we got only his-tag protein. So if we run all those sample in a HDS page, how that gel might look like. So you see, in the first lane we ran a molecular weight marker. This is a standard molecular weight. Okay. And then next lane we run the cell lysate, the sample that we prepared without any purification. You see, there are hundreds or thousands of proteins there, including a strong, intense band of protein of our interest, because uh, our protein, we like as we mentioned that this is a recombinant protein that express in other organism like E. coli or something, and there we do overexpression. That's why you see this protein of our interest, the band of protein of interest is highly intense compared to rest of the protein. Okay. So this is the cell lysate where you can see protein of our interest as a strong band. Then we subjected that protein to nickel column, and if we run the flow through, you see there that band is missing. So whatever solution coming from the nickel column through the nickel column, that solution don't have protein of our interest. What does it mean? That means all the protein of our interest stay bound to the column, and whatever coming in flow through don't have our protein of interest. And then when we eluted that protein, we see a pure protein band, and its lack of all other unnecessary impurities. So we can say, like, our protein get partially or fully purified when we elute it from nickel column. So let's discuss this nickel purification little bit in more detail. Okay. So how exactly a nickel matrix bead look like? So you'll see a inert bead that is made up of large polymer of carbohydrate like saccharose, superdex, or those kind of thing. Okay. So you see here that dark round shape uh, part of this bead represent the inert part of the bead. So this is just the matrix where we can immobilize our ligand. So that has no other function than being a inert matrix for ligand immobilization. Okay. Then there would be a spacer arm, okay, that connects the bead to the ligand. Okay. And then there would be ligand. Here it would be NTA that binds the nickel ion. Okay. So now the function of NTA or the ligand is to bind the protein. The function of the inert bead or saccharose is to be a insoluble matrix for the ligand to immobilize. So what would be the function of the spacer arm? So it turns out the spacer arm is also very important for proper purification of any protein. So if the way the length of the spacer arm is very important. If it is too short, then the protein that is interacting with the ligand would have steric hindrance with the inert matrix or separose, and that would prevent proper binding. So there's supposed to be a optimum length of the spacer arm required for effective binding of the protein to the ligand. Okay, so the optimum length is around 6 to 10 carbon atom. Okay, and majority cases it is made up of CH2 group. There are certain, like, cases we find a OH or NH2 group with that, but majority is a hydrocarbon chain CH2. Okay, so if it is too short, then there would be a scope of steric hindrance that would prevent protein ligand interaction. If it is too big even, then the ligand would be highly flexible, and that also would prevent proper interaction with the protein. So it should be a optimum 6 to 10 carbon long. Okay, so spacer arm too short, there would be steric hindrance. Spacer arm too long, they would be highly flexible, and it will prevent proper binding. So optimum length is 6 to 10 is required for the proper binding of protein to the matrix. Okay. So next we are going to discuss what are the steps of immobilized metal affinity chromatography. Okay, so the first step that we normally do in IMAC is equilibration of the column. Okay, so this is not a special step for IMAC. This is in general we do for each and every running of the column. Okay, so first step we do equilibration of the column. What does it mean by equilibration? Equilibration means we have to bring the column in a particular buffer. The composition of the buffer would be exactly same in which the protein is right now. Okay, so when we apply the protein in the matrix, protein don't get a any change. Okay, any ionic shock or like pH shock or anything else. Okay, so that's why we have to equilibrate the column with the same buffer in which we are going to apply the protein. Okay, so that protein don't face any change in environment. So that's why what we do, we equilibrate the column. So when how much buffer we are going to run to equilibrate the column, the rule of thumb is 5 to 10 column volume. What does it mean by column volume? So if the volume of my column is 1 ml, then 5 column volume means 5 ml, 10 column volume means 10 ml. So because laboratory to laboratory or with defined experiment, we change the volume of our column. So keep a standardized method. We express the amount of buffer run through the column in column volume unit. Okay. So if the column is 10 ml, then one column volume is 10 ml. If the column is 5 ml, then one column volume is 5 ml. So we normally, for rule of thumb, we run 5 to 10 column volume of equilibration buffer. The next step would be binding or sample loading. So sample loading would be done where the protein in the same buffer as the equilibration buffer loaded into the column. Okay, and let it pass through the column. So the protein that has affinity for the column, in this case histag protein, they will tightly bind to the column, and rest of the other all impurities they supposed to pass through the column and collected in the flow through. Okay, so then the next step would be the washing of the column. So even though they are not supposed to be any impure protein impurities bound to the column, but still because of charge interaction or some non-specific interaction, sometimes it just get trapped, okay, inside the column. So there would be few non-specific protein. Another thing is, you see, our normal wild type protein also have histidine. So there might be some protein which has multiple histidine. So they might have little bit of intermediate affinity for the matrix. So we have to remove all those unwanted impurities from the column by washing it with either the equilibration buffer, or we can add little bit of eluent. Okay, the material that helps protein elute from the column. Okay, in our case it is imidazole. So why imidazole is used for elution, that we'll discuss later. Okay, in our next slide. So washing, we can wash with just the buffer A or the initial buffer or binding buffer, and a increasing concentration of imidazole added into that binding buffer. Okay, so once the washing is done, so we expect that there would be no unwanted protein or impurities bound to the column anymore. So then we are going to go for elution. So in elution, so still now, whatever coming into the flow through, we are going to discard that. Okay, so we don't want things that are coming out of the column. So those are impurities. Only in the elution step, whatever coming through the column, we are going to collect it, because that's the protein of our interest. Now in this step only, all the protein that was bound to the column strongly, that is all the histag protein, they're going to come out of the column. So for as I already mentioned, for this elution purpose, what we are going to use, imidazole. So increasing concentration of imidazole, that would elute histag protein from the nickel IMAC matrix. So next, we are going to discuss about what are the different elution method for IMAC column. So as I already mentioned, that imidazole can be used for elution. Why? Because imidazole has almost same chemical structure as histidine. Okay, so that's why sometimes we use free L histidine also for elution. So because they have same or similar structure, imidazole or free histidine can compete histag protein for the binding to the nickel column. Okay, so it's kind of like, concept of competition, competitive inhibitor concept. Okay, so because they have same structure, imidazole can also bind to nickel matrix, and at higher concentration it would compete, and it can dislodge the histag protein from the matrix, and that's how the protein can get eluted. Okay, so for elution of nickel matrix, the most used method is imidazole elution. Okay, so we add higher concentration of imidazole, 300 to 500 millimolar imidazole in elution buffer. So elution buffer would be exactly same composition as binding buffer, only with 300 to 500 millimolar of imidazole. Okay, so imidazole would elute the histag protein from nickel matrix. So is there any other method by which we can elute histag protein to the from the IMAC? So there is another method. It's called pH elution. You see, histidine residue in histag, they form coordinate covalent bond with nickel. So to form coordinate covalent bond, the protonation state of the nitrogen atoms of histidine is really important. Okay, so if the protonation state change, and then N become NH plus or something, then it won't be able to form a coordinate covalent bond. So the protonation state, how can it get changed? If we change the pH of the medium. So if the pH of the medium is acidic, then those nitrogen might get protonated, and they would be no longer able to form a coordinate covalent bond with the nickel. So it will weaken the interaction between the histag and the nickel matrix, and that's how it might get eluted. So a lot of time if the imidazole is not good for the protein stability or something, then a lot of time what we do, we reduce the pH of the buffer, and that's how we elute protein from nickel matrix. Okay. So there is another popular way of elution of protein. Okay. So a lot of time when we prepare recombinant construct for the protein, there is a scope that we can put a specific protease site in between the histag and the protein. Okay, as you can see here, there is a TV protease site. Okay, so this protease specifically recognize this amino acid sequence, just like restriction enzymes. Just how restriction enzyme can specifically recognize a particular DNA sequence and specifically cut into that site. So these are specific proteases that can recognize only that particular amino acid sequence, and then show its activity only on that particular site. Okay, so these proteases would not harm the protein of our interest because these are highly sequence specific proteases. It will not chop down our protein of interest. Where it will cut? It will cut just the connection between the histag and the protein. So suppose now the protein with histag is bound to the matrix. So this red beam, think about this is the matrix, and this is the histag, and this is the connection between the histag and the protein, which contains the site, recognition site for that particular protease. So after the washing, if we load that particular protease into the column, what it would do? It would chop down the connection between histag and the protein, and then the protein would be no longer bound to the matrix, and it will get eluted. So now there is another question. So if you are adding a protease, which is also a protein, so would not it contaminate or add impurity to our preparation? So our purpose is to purify protein or remove all the unwanted other proteins. So in that case, this case, what we are doing, we are adding another protein to our mixture. So how it would get removed from the preparation? So you can see here the protease itself has a histag. Okay, so when we add this protease to our column, so protease would stay because of its own histag. It will stay to the column, stay bound to the column. Okay, so we don't have to worry about adding a extra protein or a new impurity on our protein preparation, because only cut protein, that is untagged protein, because of the protease activity, untagged protein of our interest would come out of the column. So we discussed three different method of elution from nickel matrix. So still, if we are using a imidazole concentration for elution, we can have two different way how we can elute our protein. One is we can use a step gradient, or in different step we can increase the concentration of the imidazole, like 100 millimolar, then 200 millimolar, then 300 millimolar, step by step. So it's called step elution, gradient elution method. Or if we have a automated pump that can produce gradient of imidazole, what we can do, we can create a continuous linear gradient of imidazole and keep loading it into the column. So in that case, it will have a gradient elution. So for making a gradient, we have to have two different pumps and a gradient maker. So majority of our FPLC systems that we use for protein purification, they have two pumps and they can produce gradient. So what we have to do, one pump we have to connect it with 0 millimolar imidazole containing buffer, and another pump we have to connect with a maybe 500 millimolar imidazole containing buffer, and then the pump will automatically pump the solution and mix it and make a linear gradient of 0 to 500 millimolar imidazole and pass it through the column. And based on the affinity of different impurities and our protein of interest, different protein would elute in different fraction. So in that way, we can get good purification and better resolution of our peak. Okay, whenever we are running a nickel into a column here. So linear gradient illusion is better than the step illusion. Okay. So for this, we'll suggest going through this protein purification principle and practice book by Robert K. Scoop for the reference. Okay. So one more thing. So once a round of purification is done, then what we do? We regenerate the column. Okay. And then we can use that same column for next round of purification. So how we can regenerate the column? As you can see, this is a nickel ion immobilized to the matrix, and protein, they bind to those nickel ion. So if we remove the nickel ion, then there will be less scope of any protein from our previous run stay bound to the matrix. So that's the thing we call stripping of nickel from the matrix. So we can do by applying EDTA. EDTA, you all know this is a chelating agent. Okay. So what EDTA does? It chelates the nickel and remove it or strip it from the nickel column. So if you go through that different step of regeneration, you'll see that initially, as I shown, that column was blue, and then when you add EDTA, it will strip all the nickel ion. Then the column would turn into white. Then you have to wash the column with water to remove all the leftover EDTA. Okay. So once all the EDTAs are gone, then you are good to apply fresh nickel chloride to the column, and that will recharge all the NTA with fresh nickel ions, and your column would be ready for next round of the purification. So this is the regeneration process we follow each and every round of purification. At the beginning, we do this regeneration. Then next step would be the equilibration of the column using the binding buffer. So that's how we keep running same column one after another, multiple round of purification. So this is the book for reference. Thank you.